Hi, everyone. My name is Ryan Lee. I'm going to give an introduction to PyNWB, which is the Python API for working with NWB data, for writing NWB data and reading it programmatically in Python. To get started, using PyNWB, I recommend that you, if you haven't already, search for PyNWB. One of these will be at the top, I hope, either the GitHub page or the Read the Docs page. So go to the Read the Docs page, and this will take you to the main documentation site for PyNWB. And just to orient you, we have very getting started level pages on installing various tutorials on reading and writing NWB files, adding containers, extending NWB, validating terms, and then specialized tutorials on different domains, and advanced I/O topics for customizing your chunking and compression settings, iteratively reading and writing data from and to an NWB file, modular data storage, streaming, and use of ZAR. And if you're looking for any other documentation on how to validate, export, or use the API for NWB, we encourage you to browse through this page, and you can see documentation for each individual class in PyNWB here. Okay, but for the next 20 minutes, I'll be covering the very first tutorial here, and you can follow along by navigating to this page as well. So general tutorials, NWB file basics. And yeah, so this will just give you an initial introduction to the basic concepts of an NWB file, and that includes some of our most common data types, which are time series datasets, which are objects for storing time series data, and processing modules, which are kind of groups that group together objects that's related to a data processing or data analysis. Often these include time series or specialized types of time series data, but it may include other metadata related to, let's say, a image segmentation of calcium imaging data. Okay, so time series objects store time series data, any data that varies over time, and it can include multiple variables. So if, for example, in extracellular electrophysiology, we often use probes, multi-channel probes, and so the data that comes from these probes will be oriented as time by channel, and that is the core array that makes up the electrical series data type. Now, the time series data in PyNWB follow an object-oriented inheritance pattern. So if you're familiar with object-oriented programming, you have classes that may subclass or have subtypes of that are more specialized than the original kind of high-level abstract base class. So for example, here, time series is our base object, and it specifies that all time series objects must have a name, it must have a data array, it must have either a timestamps array or a starting time and sampling rate, and it must have a description and a unit of measurement as well. Sorry, there's 5. But then for extracellular electrophysiology, we have a more specialized data type called electrical series that imposes either additional metadata fields or constrains the fields of the original time series data. So in this case, electrical series says that the units must be in volts, and this keeps it standard across different acquisition systems that may report different data in different units. Similarly, for intracellular electrophysiology, we have the patch clamp series, which is the base for all intracellular time series. And this is further refined into different subtypes depending on the type of recording that you're doing. In optical physiology, we have image series and optical series, and then 1 photon and 2 photon series. And there's a few other subtypes of time series that you might encounter as well. In this module today, or right now, we're going to cover the spatial series as a nice example. Now, processing modules store analysis data types usually, and this might include behavioral time series or any extracted features from your extracellular electrophysiology or your LFPs or your fluorescence that you've calculated from your raw images, etc. So NWB organizes data into different groups, high-level groups, depending on what type of data they are. I think we briefly mentioned this yesterday, that NWB has a high-level group for acquisition, a group for processing, a group for analysis, and a group for stimuli. And your acquisition group usually holds or is intended to hold raw acquired data that should never change. Your processing group holds any process data, typically the results of any pre-processing algorithms like running Hyman or Sweet2P, or frequency decomposition of your electrical series. And these can change depending on the parameters that you select. And there's a group for analysis for the results of data analysis and stimuli such as images, videos, and light pulses and audio. Okay, now to get us started using PyNWB, first you need to install PyNWB on your system. You can do that just by in your terminal running pip install PyNWB, and that will get you the latest version. We will set up a bunch of imports here that we'll use later on in this example. And now let's construct our first NWB file using PyNWB. So in NWB, an NWB file represents a single session of an experiment. So if your experiment has 100 sessions across all your subjects, you would end up with 100 NWB files. Now, each NWB file has 3 required fields, and that is the session description, identifier, and session start time. Oops. For the description, we recommend you place a free-form text description of something that describes this particular session. The identifier, we recommend you use a universal unique identifier, so you can just copy this string of UUID4. And for session start time, we recommend that you find out what was the earliest start time of your data recording that you intend to share, and set that as your session start time. There's a few other parameters or keyword arguments that you could pass that are useful for anyone reusing this data, which may include yourself, in the future. And this, such as who did the experiment, what lab, what institution, a description of the experiment, the keywords, and any related publications. And there's many different fields that you can specify here, and you can go click NWB file, any of these, to get to the API documentation and see all the different options that you have available. And if you were at the NWB guide tutorial yesterday, you might recognize that many of these fields you can also set in NWB guide. And one option that you have is to use the UI of guide to create an NWB file. You may not populate it with anything through guide, but just to create the skeleton structure using an easy form that you can fill out, and then you can append to it following the instructions in this tutorial that I'll describe later. Okay, so once you've created your NWB file by passing in these keyword arguments, and you just run it, then you'll get if you were to do this in Jupyter, you can get a interactive, like expandable view of the values that you've set. And right now it's just metadata, so most of it is very simple. But as you add additional data types, like your raw data or your process data, you can always print NWB file in your Jupyter instance to explore it in this kind of drop-down manner. Okay, next we're going to add subject information to our NWB file, and we'll do that by using the subject class. The subject class has 6 fields for different metadata, and I think there's actually a couple others, like strain as well. But you can specify the age, the species, the genotype, the sex, the description. And you do that in much the same way as for NWB file, just by passing keyword arguments to the class constructor. So subject, parenthesis, and then you can pass in subject ID is 001 and the rest of these. For the age, species, and sex fields, we highly recommend that you follow particular conventions, and this will help other software tools like the Dandy archive read this data and interpret it. So for age, we recommend that you use the ISO 8601 duration format, which says that the first letter is P, and then you have a number such as 90, and then a D for days, or W for weeks, or M for months. And for species, we recommend that you use the Latin binomial, such as mus musculus or Homo sapiens. And for sex, we recommend you use the single letter abbreviation FMURO in this case. And if you were to print out the subject, you would get this. And then, if you just create the subject, it's not attached to anything yet. It's not attached to your NWB file. You have to call NWB file.subject equals subject to set the NWB file subject field to your new subject object. Okay. Next, we'll cover creating a generic time series and adding that to the NWB file. So as I mentioned earlier, time series is a common base class for any measurements that are sampled over time, and it has a data array and a timestamps array often. You can initialize one by calling the time series constructor, passing in name. We recommend you add a description. You set the data to a NumPy array or a list, where the first dimension is always time, and set a unit of measurement. And in this case, let's say we have a regularly sampled time series that is sampled every second, so 1 hertz. And it will start at 0 seconds after the session start time. So we would specify starting time equals 0 and rate equals 1. So all time in NWB, all timestamps are relative to the session start time that you set earlier in the NWB file up here. So by setting a starting time of 0, that means the first data point is starting at, in this case, April 25th, 2018 at 2:30. Great. So that is our regularly sampled time series, just created this way. You can print it out and see the values here. For any irregularly sampled recordings, where you can't just pass in a constant sampling rates, you need to provide the timestamps for the data, and you can provide that as an array or a list in this manner here. So instead of starting time and rate, you just pass in timestamps equals timestamps. And you can look at it here, data and timestamps. Okay. You can add these time series objects directly to your NWB file using add acquisition if you're adding any acquired data that you don't expect to change. You can call add stimulus if this represents a stimuli information, or add stimulus template to store stimulus templates. So in this case, example here, we'll just call NWB file.add acquisition and pass in the time series, and it will be added to the file. We can verify that it's added to the file by calling nwbfile.acquisition, and these are effectively dictionaries. So you can use the square bracket notation here to get the item with the name test time series. And we set the name up here, test time series. And this will return back your time series that you added to the file. You can also use get acquisition in much the same way. Okay, now let's add some simple behavioral data to our NWB file. To do that, we're going to use the spatial series class, and that represents the spatial position of an animal over time. This can be XY or XYZ. And we will call the spatial series constructor with some fake data. We'll pass in a name, description, the data, the timestamps, and one field that is added by spatial series relative to time series is that spatial series requires a reference frame. And this is a free-form text field that asks you to describe what is the reference frame for the coordinate data in your data array. And so this allows you to say that, where is the origin point? For example, 0, 0 is the bottom left corner of my open field. Or you may have some other system that you want to describe here. So if we pass these keyword arguments to the spatial series constructor, we get an object. You can print it out just like all the other ones. And this spatial series object is kind of plain right now. It can represent other things besides position. And to help external tools know that this spatial series object represents the position of the subject, we're going to store the spatial series object inside of a position object. And this position object can hold one or more spatial series objects in the case that you might have different trackers on your animal and they represent different points. So we will create a position object and pass in the spatial series object as a parameter. If you had more than one, you can pass in a list of them here. And now we have a position object, which is just a container over our single spatial series in this example. But we haven't added this position object to our NWB file. We're going to try to add it to our to a processing module because this data is processed from a video stream. And to do that, we're going to create a processing module. Now, processing module is a class that groups together any data related to a particular processing workflow. And you can think of it as just like a folder within the file. And we recommend that you use these conventions for naming your processing modules. So any behavioral data will go in a behavior processing module. Any extracellular ephys data goes in an EC-ephys processing module, and etc. So we're going to create this module, name it behavior, by calling nwbfile.create processing module, pass a name, behavior, and we'll add a description and say this is process behavioral data. Once we have that processing module, it's part of the NWB file because we created it from the NWB file, but it's empty. So we'll call behavior module.add position object to add our position data into the behavior module. We print that out, we'll see that under behavior, it has a field called data interfaces. And within there is your position. Position has a field called spatial series, and within there you have your spatial series object with your data. Okay, and this is a kind of graphical representation of what we just did here and how these classes relate to each other. We have a processing module. We have a specific one called behavior. That's an instance of processing module. This one contains any number of any types of NWB types. And we put in a position object, and that has a spatial series. It can have one or more spatial series. And that's described by this class here, which extends the time series class with some extra restrictions in that there's a reference frame and actually that the units must be in meters. Once you've created your behavior processing module and added it to the NWB file, you can access it by calling nwbfile.processing, square brackets, quote, behavior. Okay, one more topic is covering time intervals. We're going to cover how to add trials to your data in this tutorial here. But if you want to add other types of time intervals, such as epochs or custom time intervals or any time periods that you want to exclude from analysis, we recommend that you check out this tutorial on annotating time intervals. For trials, trials are stored in a class called time intervals. And this is a subclass of dynamic table. And dynamic table is a class used throughout NWB to store tabular metadata. And this includes not only trials, but also electrodes, sorted units of your electrical series, also ROIs of your optical data, two-photon data, etc. And what's nice about this dynamic table is that it allows you to add columns to the table depending on your needs. So the trials that are used in experiments all across neuroscience vary significantly. So if you want to add trial metadata that are specific to your experiment, we recommend that you add custom columns. And these columns will not exist on other people's trials tables, but they will be in yours and be part of, still valid under the NWB schema. Okay, so the trials table structure looks like this. We have rows that represent different trials and an ID value, an ID column goes from 0 to n usually. And then there are two required fields, start time and stop time. And then you can add additional fields as well. You can add additional fields or columns by calling nwbfile.addTrialColumn. You can see that here. Just give it a name and a description of what this column represents. And now this column is added to the table. That also means that every trial that you add to the table must have a value for this column. So we'll add trials by calling nwbfile.addTrial, pass in a start time, stop time, and then we're going to say that this trial was correct. And the next trial starts at 6 seconds, stops at 10 seconds, and is incorrect. And we could put this in a loop to add all of the trials from your original data source. You can view the contents of your trials table and interact with them easily by converting it to a pandas data frame. If you're familiar with pandas already, just call nwbfile.trials.toDataFrame, and you'll get a data frame representation of your trials table. Great. Lastly, in this tutorial, we're going to cover basic writing, reading, and appending. To write an NWB file, we've been adding contents to this in-memory NWB file object. Now we want to write it to a file. We're going to call to make use of this class called NWB HDF5IO. And HDF5 is the backend that we're using. We're creating HDF5 files, which are common in scientific data. And we're going to pass it a file name here and pass a mode to say that we're writing as opposed to reading or appending. Once we have this IO object, we can call io.write and pass in our NWB file instance, and then close the object, close the IO object. You can also use this NWB HDF5 IO as a context manager by saying with this object as IO, and call io.write, and then the object will be closed at the end of execution of this context manager. And then you will have a NWB file with your subject information and your spatial series and your trials. Now we can read this file. We will use the same class, NWB HDF5IO, but this time we'll pass mode equals R. And instead of io.write, we will call io.read, and we'll get back an NWB file object. And then we can explore this NWB file object in much the same way as we did earlier. We can call .acquisition on it and pass the name of a time series, let's say test time series, to get this printout of the fields within that time series. Importantly, data arrays are read passively from the file. So your data of this time series may have millions of elements, but calling .acquisition test square bracket test time series doesn't actually load those millions of elements into memory. But it will show you the metadata and have a pointer basically to those data. If you call read NWB file .acquisition at test time series .data, you'll get this HDF5 dataset. And if you index it using square brackets : then it will load all of the data array into memory. And we can print that out and see it here. Now, usually it's often, you often want to read only a portion of that data because the data is really big. And so to do this, you can index or slice into this data attribute just like you would slice any NumPy array. So this here will get the first two elements of your data array. All right, and the last bit here is how to, one more part about accessing data is you can access your spatial series data, which lives in your processing module, by referencing the names of the objects in the hierarchy that contain it. And if you remember earlier, the spatial series is nested under the processing module called behavior. So we'll call read NWB file.processing at behavior. Within that behavior, there's a group called position, and within that position group is an object called spatial series. So you can explore the NWB file this way. You can also just print the read NWB file if you're in Jupyter, and you'll get the same drop-down menus that you can, expandable menus that you can click. Lastly, we'll cover how to append to an NWB file. In this case, instead of setting the mode to R or W, you would set it to A for append. And you would read in your NWB file object, and then you can create new objects. So in this case, we're going to create a new time series, and we're going to add it as a new acquisition to our NWB file. You just call .add acquisition, just like when we were creating it initially. Finally, we'll write the changes back to the file using io.write, and then close the IO object. And that's it. That covers creating an NWB file object using PyNWB, creating a subject object for your subject metadata, creating a spatial series object for your position data, and adding it as a processing module into a processing module in your file, adding trials to your file, and then writing the file to disk, reading the file from disk, and appending the file, appending to the file. And this is all using PyNWB, and I'll pass it to Ben, who will cover the MatNWB side of this same tutorial.
So we're going to be going through a lot of the same stuff that Ryan just went through. I'm just going to show you the differences in syntax, a few small differences. First of all, how do you install MatNWB? You git clone it. So this exclamation point will run command line commands from MATLAB. So you don't have to go to a terminal or anything to run it. Though you can run this in terminal, you just would not put the exclamation point. Git clone, and then here's the repo for MatNWB. And then to install it, all you need to do is add it to the path. So I like to do gen path of my working directory and then add all of that to my path. There are other ways to add it to the path, whichever way you normally install things, but this should work. Okay, so the first thing we need to do is create the NWB file object. We do that with this NWB file command. Oh, by the way, these links will lead you to like API documentation, which will tell you about all the different input arguments you can use. So the first thing you do is call NWB file. Make sure you call it like this. And so we input the arguments here as key value pairs, which you're probably familiar with as a MATLAB user. So it's a session description, identifier, session start time. Here's how you would do a date time with a time zone. This syntax you might not be familiar with. This is just continuation of this line onto the next line. So it just allows us to format these long calls a little more elegantly. One of the differences is the naming of things is slightly different. So in PyNWB, this is just experimenter, and in MatNWB, it's general underscore experimenter. That's because that's actually where it is in the file. So MatNWB is it names things according to where things are in the resulting NWB file. So when you create this file, experimenter goes within the general group. So here it's called general underscore experimenter. And the reason it's different is actually MatNWB takes the schema and generates classes based on the schema. So it's all kind of procedurally generated. Which means we don't have as many convenience functions, but it's kind of, there's this nice one-to-one mapping with the actual data schema. So it does mean though that occasionally we have to write a few more lines of code. So, and this is one of those cases where you just have longer variable names. Okay, last comma first name for experimenter, session ID, institution, related publications. And then if you run that, you get this NWB file object, which will show you all of a lot of empty fields, but also a lot of the ones that you filled in. Okay, then the next thing we want to do is create a subject. This is done similarly to the way Ryan showed. The variables are the same. The variable names are the same. So you would do, to access these types. So you might not be familiar with namespaces in MATLAB. It's a bit of a more unusual feature. But basically, that's what these periods are doing. So we have a namespace called types, and then a namespace called core, and then the class corresponding to the neurodata type. This allows us to have extensions that are also automatically generated and aren't in the same namespace as core. So it just allows us to separate out things a little bit. That's all these periods are doing here. It's just kind of traversing the folder structure. If you look at the actual code that's downloaded, let me get the way that these namespaces are done in MATLAB is you put this plus sign before the folder name. So if I go in here to types and then core, and then here's where all of our core neurodata types are, and then I can find subject. So here's that subject class that we're using. But this is automatically generated, and generally you don't need to edit this at all. All right. Okay. So subject ID 001, age again should be in ISO 8601 duration format. So this means period of 90 days. Description, species should be Latin binomial. Sex should be F, M, U, or O. And then you can add that to the NWB file like this, NWB, which is the result of this call. Dot general subject equals subject. So that will add it to the NWB file. And then I'm just printing out the subject information here. You can see there are a few fields that I didn't populate: genotype, strain, and weight. Date of birth, generally you would either include the age or the date of birth. You generally wouldn't include both. Okay, so just like PyNWB, you have this concept of time series, which is the base type for lots of different types of specialized time series, and also can be used on its own. It can handle regularly or irregularly sampled data. If you have regularly sampled data, you use the starting time and the rate. So that looks like this. You would use types.core.timeSeries. You give it a description. You say what the data is, the data unit. So this is, again, different from PyNWB, where this is just called unit. Here it's called data unit because in the actual file, unit is an attribute of the data set. Starting time, it would be 0. And this is a bit of a weird syntax here, but in order to specify the rate, it would be starting time rate, because rate is an attribute of starting time. It's a bit counterintuitive, but it works. Another thing to mention here is that the orientation of the arrays is the opposite in MATLAB. So in Python and NumPy use C-ordered arrays, and HDF5 uses C-ordered arrays, but MATLAB uses F-ordered arrays, which is like the opposite. So in order to get them to be able to result in HDF5 files that have the same shape, you need to actually reverse the axes in MATLAB. So for time series in Python, the 0th axis or the first axis is time, but in MATLAB, it's the last axis that's time. Okay, so then here's how you would do it with starting time and rate. And then here's how you would do it if you have timestamps. You would omit the starting time and rate, and instead you would put timestamps. Okay, let's move on. Any questions so far? So these neurodata objects are not I didn't put these into the NWB file. This is just for illustrative purposes. Normally when you create these, you would need to then add them to the NWB file. So I'll show you how to do that here. So here's how you would add some behavioral. Let's say we had spatial series and position data, or spatial series data which is position data. I'm using this UML diagram here, which shows that spatial series subclass is time series and adds reference frame. And then there's a position object which contains spatial series. So these arrows are like a kind of an official diagramming language. This means that this square or diamond, I guess, means that spatial series are contained within position. And then this open triangle arrow means that spatial series extends time series. Okay, and you can look more at about those diagrams here at this Wikipedia page. Okay, so since spatial series is a subclass of time series, that means it requires all of the same attributes of time series. So you require data and timestamps. And then it also includes this reference frame. So we're just going to make up some data. This is just linear example data for both the data and the timestamps. Now here I'm using, I'm creating fake data that's regularly sampled, which if you have regularly sampled data, you probably should use starting time and sampling rate, not timestamps. I'm just doing this to illustrate the point. But the dimensionality of data and timestamps should match in the last dimension because that's the time dimension. So then you can create this position object, which again you would call types.core.position. And then here's actually where you name the spatial series. So this is another difference between Python and MATLAB. So on the Python side, you name the object as you create the object. On the MATLAB side, you name the object as you set it to its parent object. So here you're saying, okay, yeah, to the position object, add this spatial series time series object and name it spatial series. Then we're going to create this module and it's going to be a behavior module. And we'll just say in the description that it contains behavior. This is, again, a bit different syntax from PyNWB because you actually have to create this processing module class, this instance of the processing module class, as opposed to just saying NWB file dot create processing module. But okay, and then this behavior module has this attribute NWB data interface, and we can set the position object that we created, and we'll just call it position. So that's kind of the default thing that I like to do is if you just have one of a certain neurodata type, and you want to add it in, what do you name it? I just name it the same as the neurodata type. Now, if you have multiple of these, and you're going to have to name them different things, but in this case, you just have one, so it's not a problem. Okay, so then we have a processing module, and we've added the position object to that processing module, and we've added the spatial series object to that position. So now the last thing we need to do, I guess this is a bit of repeated code here. The last thing that we need to do is add this behavior module to processing. So we're going to add it to the NWB file .processing. We're going to call it behavior, and we're going to add this behavior module that we created here and add it position to. So now finally we have an NWB file. The NWB file contains a processing module called behavior. Behavior contains the class called position, and position contains the spatial series data, spatial series object, and then that spatial series object then contains the position data and the position times. All right, let's move on to trials. This is another thing that you might want to add in MatNWB. So just to explain this diagram here, so we have this generic type called dynamic tables that can handle just any, it's just like a generic table type that stores tables in a columnar fashion. So every column is a data set. Then this is subclassed by time intervals, which defines a start and stop time. And then trials is an instance of this time intervals class. So it will end up looking something like this, where you have an ID for each trial, a start time, a stop time, and you could potentially add more optional columns. This is really useful because there's so many diverse different types of trials and different ways of parameterizing them. So we have this just start and stop time, and then any other features about the stimuli or about the responses or the conditions of the trial can be added in custom columns here. So just to demonstrate that, we're just going to add a correct column, which we'll take Boolean values, true or false. So I can create this trials table with the time intervals class, define the column names. I have to define start and stop time, and I'm adding correct to that. And then I can specify a description for this trials table. And then you can simply add rows. Yeah, you can do add row, start time, stop time, correct, start time, stop time, correct, start time, stop time, correct. And then at the end of this, you can do trials.toTable, which prints out this in a nice, this is like a newer built-in MATLAB type is like this table type, which has a really nice printout here. So you can get a nice view of the table with that. And then I think what I've actually forgotten to do here is add this to the NWB file. So, I just modified this last night, and I think I forgot to do that. So let me just open this up over here and show you what that looks like. All right, go to tutorials, intro. All right, and then if I go down to here. Okay, yeah. So it would just be NWB dot intervals underscore trials equals trials. I'll make sure to add that to the tutorial after I finish this, but that's going to assign the trials to the NWB file. Otherwise, it's just kind of floating around and it never gets saved within that NWB file. Okay, once you've done all that, you can write it. So that's as simple as just calling NWB export with this NWB file object that you've assembled all of these neurodata classes into, and then you just say what the path of that should be. Intro tutorial.nwb is what I'm using here. Then you might want to check out that file. I like the software HDF View to do this. You do have to register in order to download it, but it is free and it's a really nice way to explore this. So this is generally what the view you get there. So you can kind of navigate into groups as if they were folders, and you can double click on a data set and it'll show you the values of that data set, and you can just kind of confirm that everything looks the way you expect. To read NWB files, I'm just going to read this back into memory and call it read NWB file. And you just say NWB read, and you give it the path. You can call ignore cache if you already have. So the cache is defining a schema, which then is used to generate these classes. If you've already generated the classes, you don't need to do that. So you can just call ignore cache and it'll read it a little faster because it doesn't have to regenerate all of those classes. And okay, so how do you read this data? So if you go, you have to do a little bit of traversing here because we had a pretty nested structure for storing this spatial series data. But if you do read NWB file dot processing dot get behavior dot NWB data interface dot get position dot spatial series dot get, okay, and here's the name of the specific spatial series. This finally gives us that spatial series object that contains the reference frame, the data and the timing, which not quite sure where the timing is here, but this contains all the data that you want. So you can then and then you do this read spatial series dot data. This gets you a data stub object. So this actually doesn't even read the data. It just tells you information about that data set. So what the file name is, what the path is, the dimensionality, what data type it is, but it doesn't actually read that data in. If you want to read that data in, you call data.load. And the reason for this is this is not done, well, the reason for this is the data might be huge and you might not want to read it all into memory. So this infrastructure, this tooling allows you to read in only segments of the data. But we also want to make it convenient. If you do want to read in all the data, you can do that. You can just say .load and it'll read all the data. But if you don't want to read in all the data, if you want to only read in a subset, you can do it like this. You can say read spatial series, spatial data, sorry, read spatial series dot data, and then you can index it just like you would index a normal in-memory array or matrix. And this will actually, even though the syntax is similar, what's going on here is it's actually only reading these this region of the data from disk. So, so here we're only reading this 2x10 data set from disk. If this were hours long, then it would be really helpful to be able to only read a certain amount from disk. So that's what we call like lazy reading or direct access reading. And yeah, so that makes it slightly trickier because it takes you an extra command to actually get to the data, but it allows you to be much more economical about how you read it. Okay, so that is the MATLAB side of the intro tutorial.